Here's a question. Can you mathematically reach a point moving in a straight line? Seemingly easy to answer, you just see a point and you go there. This question was basis for an idea formulated by an ancient Greek mathematician Zeno. It postulated that you will need infinite amount of half steps to reach any given point. While this may seem bizarre, what you certainly know is that you are getting closer. So the question becomes, how do you quantify how close you are getting mathematically? The answer to this question was formulated centuries later by a mathematician Karl Weierstrass, also known as the father of modern analysis, who despite his accomplishments is still not as known outside of mathematics as he should be. In fact, he is the man who was able to rigorously quantify the notion of convergence. Weierstrass never actually studied mathematics formally at the university. He graduated with a public finance program from University of Bonn. After graduating University of Bonn, he went to Theological and Philosophical Academy and was able to visit the lectures of another mathematician of that time, Christoph Gutermann. At the academy, Karl was able to make significant contribution to a theory of elliptic functions as an answer to one of the papers that he was presented with. Gutermann himself has said that Weierstrass' contribution was of the equal rank with the discoveries that were crowned with glory. Instead of getting himself into research, he spent 14 years teaching at the gymnasium, conducting his research independently before finally publishing his famous paper on the theory of abelian functions. So how he was able to quantify this notion of convergence? Here's a simple example. Consider a sequence of numbers that begins with 1 and recursively adds powers of half and goes on forever. For those of you familiar with series of such form, you might recognize it as a geometric series, and the formula for the final sum of the first n terms of such geometric series is given by this. Now, what if we want to consider the sum of the entire sequence, that is infinite number of terms? Setting n to infinity, we get that in the expression above, 1 over 2 to the power of n goes to 0, so the numerator of the sum goes to 1. But what does it mean for n to reach infinity? Here's when the Weierstrass genius came in. By reformulating the question from what does it mean for a sequence to reach a limit, to after a given term in the sequence, how close to a limit is the sequence, Weierstrass was able to answer this exact question. Formally, Weierstrass defined an infinite sequence as having a limit if for any epsilon you can find an integer n so that for all integers m that are greater than n, the mth term of the sequence is always within the distance of epsilon of the limit. It is easier to see what it means when applied to our example above. What does it mean that the sequence half to the power of n goes to 0? This sequence can be illustrated as follows. We can now consider any arbitrary distance from 0 and call it epsilon. It could be this, or this, or this. For a sequence to converge to a limit, it would mean that for any such epsilon, we can find a term in the sequence such that after this term, any other term in the sequence is also less than distance epsilon away from 0. This seemingly simple idea provided the basis for the notion of convergence and limit, and by thinking about how close to a limit is a sequence compared to previous term in the sequence, we can formulate mathematically the idea of convergence. It had tremendous impact on the world of mathematics, but it had particularly good impact on the theory of functions. To be more specific, it allowed for mathematical description of continuity. Intuitively, a function is continuous if you can draw it without lifting a pencil. Here are two examples. This function is continuous, and this function isn't, because there is discontinuity at point x equals to 2. But what does it mean mathematically? Consider a function mapping x to the power of 2. A function is said to be continuous at a point x0 if for every epsilon a delta could be found, so that f of x is within f of x0 whenever x is within delta of x0. This definition certainly fits the intuitive notion that as you draw a continuous function near a point, you had to be getting close to a value of a function at that point. While this may all seem fairly uninteresting to a more practical viewer, in reality these ideas are so groundbreaking that are applied in virtually any modern scientific field. One simple example is used by computer scientists and machine learning engineers to solve optimization problems, trying to find a minimum or a maximum of a given function. Say that we have a complicated function f of x, then an optimization algorithm, like gradient descent, would take a discrete steps starting from f of x0 and continue to f of x1, then to f of x2, and so on, getting closer and closer to the true minimum or the maximum of the function. Weierstrass' framework allows engineers to compare different such algorithms and see how fast a given sequence f of xk approaches a true minimum. This, of course, is just a simple illustrative example of how this approach helps us mathematicians and engineers analyze functions better. There are many other fields where this plays a key role, ranging from signal processing to quantitative finance. Weierstrass' work on this epsilon-delta definition of limits and continuity revolutionized the field of mathematics. His rigorous approach not only clarified the foundational concepts, but also enabled advancements in various scientific disciplines. He also contributed to other important results in analysis, like Bolzano-Weierstrass theorem, that states that convergence of a subsequence exists for every bounded sequence of real numbers, worked extensively on theory of complex functions, and as mentioned previously, contributed to the theory of elliptic functions. Truly, it is really hard to imagine where mathematics would be today without his ideas.